In this video, I would like to summarize some of the new quantities we have learned in relationship to some of the ones we knew before to help kind of, build out this network of connections between related ideas. All right, so first of all, we started with Coulomb's law. So the force between two particles is equal to k q1 q2 over r squared, r hat. All right, and from that, we developed this idea of the electric field. So the electric field for a particle is k q1 over r squared, r hat. All right, and by analogy with these, we had the electric potential energy, which is k q1 q2 over r, and the electric potential, which is the electric potential energy divided by the test charge. So what that will look like for a point charge is just k q1 over r. So kind of looking at the variables for this, the formulas for these different quantities, we can see that as we went, we've really done a pretty good job of simplifying things. So the most complicated formula here is the one for force, and then it gets easier and easier as we get down to potential, which has just one charge and just one r in the denominator. But there are more connections than that between these. So if I make this into a table, like so, then I can see that there are some relationships between these quantities. Okay, so across the top, I have two vector quantities, but the ones along the bottom are scalars. Okay, and as we know, scalars are easier to work with than vectors. On the left-hand side, we have two particle interactions. So both forces and energies are things that occur only if you have two particles. They don't really make any sense if you just have one. And on the right-hand side, we have one particle properties. So by thinking of an electric field instead of an electric force, we're able to only consider one particle at a time, which simplified things quite a bit. The same thing is true for electric potential. The potential is just a property of one individual charge, and we can find the potential if we have a bunch of different charges present, but we find the potential for each one and then add them together. We have a variety of connections between these. So the connection between the force and the electric field was given by the definition of the electric field. So essentially the force is the test charge times the electric field. Similarly, we defined the potential so that the potential energy is equal to the test charge times the potential. So if we know the potential, we can find the potential energy and vice versa. The way that we connected force and energy was by using the definition of work. So work is related to energy, of course, and the work is equal to F dot D, so the force times the displacement. We didn't go the other way in this course, but in 121 you also saw that the force, we can do it one component at a time, so let's say the x component of the force is equal to du by dx. And that needs to be negative in order to make the direction correct. But we can actually take a potential energy as a function of position and then use it to calculate a force. Okay. So we have not yet explored the relationship between electric field and potential, but we'll find that they are actually closely related. And that's going to be one of the things that we study in the next few lectures. So another thing to notice is that as we go from the upper left of this diagram to the lower right, the formulas get simpler, but in some ways the concepts become more abstract. So forces are very easily understood. You can see a particle being pushed by another particle. You can feel a push or pull. So that's very concrete in that way. Well, potential is this sort of invisible property, and we can only measure potential differences, and it has all these weird caveats going on with it. So, one of the payoffs of learning some of those more abstract ideas is it makes the calculations a little simpler, and it makes some of those relationships that may look complicated make sense in terms of simpler rules.